You can get the other questions online. And we need to move to the next question, the next presentation. Kimberly Reid, she's a postdoc at the ARC Center of Excellence for Climate Extremes and based at Monash University, and we'll be talking about forecasting rainfall at multi-week timescales using the ACCESS-S2 and atmospheric readers.
Thank you. Cool. Thanks. Hi, everyone. I'm Kim Reid. I'm a new postdoc with CLEX and Monash University. And also thanks to Debbie Hudson, who helped out with some of these slides. I'll be talking about sub-seasonal to seasonal forecasting. So for those who aren't familiar with this, S2S or sub-seasonal to seasonal forecasting sort of straddles the space between numerical weather prediction and climate projections in terms of spatial and temporal scales. So while your numerical weather predictions kind of go up to about a week and a much higher resolution, and your climate projections are sort of years, decades, centuries, and obviously much coarser, S2S models try and make projections between 1 week to 9 months. And this is, of course, potentially extremely useful to a variety of industries, the obvious ones being agriculture, emergency management, insurance, construction, and energy resources even. So, for example, New Zealand hydro energy has about 6 weeks worth of stored energy in terms of water in their dams that they can turn into energy. So knowing what the rainfall is going to be doing in the next 6 weeks is extremely important for planning ahead in those sorts of industries. Now, with lead times to 1 week to 6 months, you're not going to be predicting an individual thunderstorm or cold front 9 months in advance. Instead, you sort of predict whether you're likely to get above or below average temperature rainfall on kind of weekly timescales. So in Australia, we use ACCESS-S2 as our seasonal forecasting system, which uses the UK Met Office's global climate model with some tweaks. So there were some issues with drainage into inland lakes, which has been fixed. There are a few ozone errors that have been fixed. And in ACCESS, the coupling is more frequent. So it's 1 hourly instead of 3 hourly. And it's been operational since late last year. So the ACCESS-S2 forecasting system uses the Bureau of Meteorology's weekly coupled data assimilation and initial conditions. So for S1, they're actually using the UK Met Office's initial conditions, which in some cases was just the climatological value. So in S2, one of the key improvements was to the data assimilation and initial conditions. And this then feeds into a global climate model and produces an ensemble of forecasts. So here's sort of the Frankenstein's monster global climate model. It contains the atmospheric model, the Joules land surface model, NEMO 3.4 ocean model, and the sea ice model. And these are all coupled every 1 hour. I won't go into super details. You can read the resolutions for yourself, but it's sort of 1/4 degree, 1/2 degree resolution. Cool. So as I said before, you're not going to be predicting an individual storm weeks in advance, but the predictability in an S2S model comes from the teleconnections between modes of variability such as ENSO, IOD, MJO, and SAM, and the variable of interest, so temperature or rainfall. So if you have strong teleconnections between ENSO and rainfall, then you're likely to get a better seasonal forecast. So how I'm actually using this is where I'll, whoops. For those online, our projector just decided to say goodbye.
Oh.
Oh, great. Don't worry, I should be under time. All righty. Cool. So the motivation for what I'm doing largely comes from some previous studies out of Europe that showed that using the large scale movement of moisture, you can actually can sometimes be more predictable than the precipitation itself for predicting extreme rainfall events in numerical weather prediction models. So this is sort of short to medium range, 1 to 2 week time frame. You can actually get maybe 1 or 2 days extra lead time if you use the large scale moisture rather than the precipitation itself, just because the precipitation, I guess, is more prone to initial conditions and perturbations, whereas the large scale movement of moisture is less influenced by these perturbations and chaoticness, I guess. That was on numerical weather timescales. Additionally, we've shown that atmospheric river frequency can be modulated by ENSO, IOD, and the NJO over Australia, and they can be associated with the extreme rainfall. So that led to the research question: can we improve the predictability of extreme rainfall at 2 to 4 week lead times using the large scale movement of moisture around the globe, which we call atmospheric rivers in this case? So the first thing we want to know is, can a seasonal model even see an atmospheric river? And while in practice you wouldn't use a seasonal model on daily timescales, because you'd sort of look at weekly totals or weekly averages, but we just want to see whether ACCESS can even produce these weather systems. And we found it actually did quite all right. So this is just a random day in ACCESS, and on the left is the integrated water vapor transport, and the magnitude doesn't really matter, just green means high, yellow means low. And on the right, we have the identified atmospheric rivers, and you have about 5 or 6 on the globe in the mid-latitude storm tracks, which is what we see in reality. So we're quite confident that ACCESS can see these weather systems. Then we wanted to look at this relationship more generally. So this is just the correlation between weekly total atmospheric river frequency in Era 5 and ACCESS-S2 in spring. We chose spring because, of course, the strong ENSO connection means we tend to get better S2S forecasts. And of course, the correlation decreases with time, but you're still getting correlations at week 4. But what we want to know is whether we can actually predict weeks of high atmospheric river frequency in ACCESS-S, because if you've got a lot of atmospheric rivers hitting a location, you're likely to get high rainfall. So this just shows the probability of detecting weeks with high atmospheric river frequency, again in spring. So 1 means the model is able to predict everything, 0 means it got nothing. And as you can see, week 1 is obviously the best, and skill does decay, but it doesn't decay that much. It's quite similar between weeks 2 and week 6. And what I haven't shown, but I will note, is that you do also get quite a lot of false alarms. So while you get the hits and often fewer misses by using the atmospheric river frequency in the model compared to, say, precipitation, for example, you also tend to get a lot of false alarms, and this is what we're dealing with at the moment. That's a very brief overview of some of the work. I want to step back and talk about potential improvements that the ACCESS-NRI might be able to help with. So one of the key issues with ACCESS-S, or the seasonal forecasting model, is that we're a very small community, and users outside of the Bureau can typically only use the output data. We can't run experiments ourselves. So the NRI could potentially provide training and support for users outside of the Bureau to run experiments. This would allow us to do a lot more sensitivity testing and potentially identify ways to improve the model even more. So to conclude, ACCESS-S2 is the current sub-seasonal to seasonal forecasting model used operationally by the Bureau. ACCESS-S2 can produce weather systems like atmospheric rivers and a realistic AR climatology, which has potential for improving our rainfall forecasts on weekly to monthly timescales. Using atmospheric rivers to forecast extreme rainfall does actually have some skill, but it's not necessarily better than the model precipitation, unfortunately. I haven't obviously shown the details of these results, but I'm happy to chat more at lunchtime. Otherwise, are there any questions? Yes, sorry, I didn't say that. So it's a 27-member ensemble. So it's a lagged ensemble. So you've got 9 ensemble members that are run on day 1 of the month, and then the 31st of the month, and then the 30th of the month, and you can lag it to create a bigger ensemble. Yes.
That was really cool, Kim. In your maps of probabilities, I noticed these very zonal structures. Do you know where they come from? There's a very, high probability line at whatever it is. I can't see that from here, 40 south, 45 south or something. And then there's a gap, and then there's another high probability. It looks all quite zonal. Do you know? Is that just sampling, or is there some physics going on, or some problem with the data?
Yeah, good point. So the atmospheric rivers tend to occur in the mid-latitude storm tracks. So you would expect some zonal movement. There is that weird feature around 40S in the Southern Ocean where there's almost like a split between the more mid-latitude and polar systems. But yeah, I think most of it's just because they move with the mid-latitude storm tracks.
Yeah, another question.
Hi, Kim.
Hey.
I was surprised to see that ACCESS-S2 doesn't actually have any Australian developed models in it. It has Jules and Nemo. So I was wondering, do you think ACCESS-S2 is actually ACCESS and that it should be supported by the ACCESS-NRI? Or is it just a jumble of models by the Bureau? Yeah, I'm just looking for your opinion as a community member of ACCESS, whether or not it should be supported and what needs to be added to ACCESS-S2 to make it more catered to an Australian climate.
That's true. And I'll be honest that I haven't run any ACCESS models yet. So I'm a very new community member. So there are a few tweaks to the original UK Met Office version that kind of makes it our own. So it uses the Bureau's data assimilation, and that has considerably improved the model. I don't really know, to be honest, but I guess it's our only seasonal forecasting model. And I think there's a lot of cool work that can be done in the seasonal forecasting space. So it would be good for Australia to have that capability.